So today we will talk about the electronic structures of solids. On last week, we discussed on quantum mechanics and how the energy of one atom can split the energy of the electron and give some discrete energies that they can be filled. So today we will more discussing on the materials aspect, how we have metal, for example, how can we distinguish metal from isolators and semiconductors. So this will be the focus. Here I will give a brief introduction on how can we explain the materials properties regarding using bond theory. So we have some inside bond theory, we have also group theory that could be used to describe how the states are doing. But here I will give just an overview on how we can discuss and distinguish the electro properties of materials regarding his states. So we will have a overview on metals, conductors, semiconductors, and isolators. And in these topics, we give some focus on how the energy bands are created, how we can know the energy gap of the materials, the difference between indirect and the direct band gap in semiconductors, and how it could be affect the carrier transport and the scattering of the carriers of the materials. So last week, I don't know if the figure is clear here, yeah. But last week we discussed regarding one atom. So in one atom, depend of the number of electrons that has in this atom, we have some energy that the electron can be accepted. So for instance, we discussed regarding the hydrogen. So we have the energy in terms of position here. And here is the position, but we can also distinguish position in terms of key vector. That means the position of the atom in a lattice of solid, if you have a period lattice. And for hydrogen, for instance, here we have the electron occupying this orbital, this atomic orbital, and when we use light, we can use this light with this energy called hν, because if Planck constant plus frequency, so we have this energy in this photon. If this energy can give energy sufficiently to the electron, this electron goes to higher energy, so it goes up, and then it comes down and emits some energy with the same energy as the photon. So we saw, for instance, in terms of absorption and wavelength. we have a discrete transition in absorption, because just this energy here, the specific energy here, will give this transition, because we are seeing just one atom. When we have several atoms, so the atoms can be, the nucleus of the atom can interact with another nucleus. And if we have several atoms with the same structure, this energy splits because of the energy distribution of the electron over the lattice of the atom, that it depends of the atom composition, and also how can he organize in terms of lattice. So if, for instance, we could join two atoms, that they can have some chemical bonding between them, covalent bond. So the energy of one atom will be split in two, and we have this we call bonding and anti-bonding energy. So we have the energy that can fix the atom together, and the energy of electron that can split them apart. So, for instance, here, in terms of the here two atoms, I'm using this set. I don't know if it's set in English, but it represents the electron with spin up, and this is the second atom with one electron with spin up in the vacance, in the valence orbital. So when we have they come doing some chemical interaction, for instance, covalent bond, here in terms of the distance and energy, the interaction of two electrons will create this split in energy. So here is not in terms of the physics, I cannot write this because I'm converting the spin, but what I can say to you is, when we have two atoms and they can with covalent bond, the electrons will create a state that we call bonding state, bonding, and anti-bonding. So in terms of light interaction, when we use excitation with some photon with energy Hν, and this energy has enough energy to move the electron from one state to another. We will move this electron here to high energy because of the perturbation. So this split in energy comes from the interaction of two atoms. If we have three atoms, it will split even more because there is interaction between these two, and then if we have some infinite atoms, we will have some band distribution, because each atom has molecular interaction, and it will give some molecular levels here that can be split inside of this band. So we also have bonding band and anti-bond band, but now in terms of the material, here we call it as conduction band, and here a valence band, and here is the conduction band. So when the electron, for instance, are in anti-bond, that is conduction band, the electron can move freely into the lattice, because there is no molecular trapping them inside the molecular structure. So what we will discuss here today is how we can know this valence and a conductor band, and how, in terms of physics, we can predict in one material if the material can act as an isolator or semiconductor or metal, and how we can distinguish if there is some aspect in terms of carrier, because when we move the electron, for instance, we will have an electron free to move inside the material. So we can measure, for instance, his mobility, his scattering also. So in terms of physics, we'll focus on bond construction, but we'll also distinguish it in terms of how we can manage this band and construct one devices that could be useful for us. So this is just an overview of what I talked, but yeah, this overall of the atoms, it will give some quasi-continuous energy band, that one split in energy here is just because of thermal modification. So this is because we call quasi-continuous energy band. So here I just give another overview on states that we have in terms of over orbital, depending of the material. For instance, here I just grab one orbital that comes for carbon, that because we work a lot with carbon. So carbon has the s orbital and p orbital because of the Pauli distribution. So in terms of the how many orbitals can electron fill, how many orbitals are filled, we follow the Pauli distribution. So in terms of carbon, we have the s orbital totally full, and the p orbital that is not totally full. So the p orbital will participate of bonding, but this orbital, because of electron distribution, will direct affect how this orbital can interact with another orbital in another atom. Is just a brief overview, because I will also talk more about carbon in the next days. But what I want to say, when we have this distribution, this discrete distribution with overlap of molecular orbitals, we will have energy gap between the S state and the P state. And if there is some atom that feels more state, they will also have a gap between those states also. So the energy gap in terms of S is higher than in terms of P for carbons. And then we can also have a different gap energy in terms of transition between states. But in this specific physics, we don't use it for devices. We just movement the electrons from the last orbital field that calls that we can use the light in the visible to manage the interaction between the materials. So just to give a brief overview what I talked, to know what kind of energy that we have allowed, we use the Bloch theorem that we discussed on the last week. So applying the potential that we can know in terms of the molecular composition of your material, we can know the energy that is allowed for our system. So here we can see, for instance, applying the Bloch solution that we talked. We know that the solution will depend in terms of K, that is the direction of the lattice. So in the direction of lattice, we can also convert in terms of distance between the atoms. So if we have two atoms and we go in higher distance, these atoms can break, so that we will lose the energy bond, the bond that stick the atoms together. And because of this separation, we can split the energy that is different when they are close. So in terms of the equilibrium, we will have this kind of distribution here. I'm just giving you this crazy graphic here, but it's just to talk because in terms of a semiconductor, what we must know is the density of states, that is called DOS. So to know if one material is semiconductor, is metal, is an isolator, we must know the density of states. So the density of states will depend the position of the atoms and the energy that we are observing. So how we can create, for instance, this shape, how it arises this value of energy, and we will see it today. So, for instance, here, if we have some, this is the lattice spacing in silicon crystal. So this is the energy that the minimum energy of the electron. So it will give the equilibrium of the atom in this position. So if we see here, we can have one electron filled, and we know if they are filled because of the Fermi distribution. But if we increase the distance, the energy of state will be more discrete than this one. So this is everything that's coming from the interaction of the electron with the lattice of the material and the composition of this material. So what is density of states? Density of states, those, they will give us the number of states per unit of energy in terms of the lattice potential, the lattice of the material. So we have the number of the states that are allowed for our electron to be filled, and we will also have this number of states in terms of the atomic position of the material. So will depend if we are analyzing one dimension, two dimension, or three dimension. And this will give us the band dispersion that we can see, for instance, the energy that are allowed in terms of materials. But the density of state do not tell how many states are available, because this we can just know knowing the number of electrons of the material and following the Fermi distribution that is similar what we do with Pauli distribution. And also do not say if these states are occupied or not. So the density of states just tell us how the states are organized in terms of material. So for instance, if you synthesize new material, the density of states, they are usually used in terms of simulation to predict and to know if the material that you are synthesizing has some semiconductor behavior or some metal behavior in terms of the thickness. So you can predict in advance of synthesis using density of states. And to prove also the density of states, you must use photons with several energies, depending of the composition of your material, but you must start from high energy to low energy. You don't have a density of state just in the valence or in the conductor band. You know it in all states that are allowed for the electron of your material. And the distribution of the density of states is filled using Fermi Dirac distribution. So it will say if you have, for instance, 2 electrons, so 2 electrons are allowed to occupy one orbital. If one orbital has 1 electron up and 1 electron down, that and the next rule is that we also have a Fermi level, that is the probability to find the last electron in your material. So the Fermi level is fundamental for us to know how to construct devices, because when you create one interface, the Fermi level will be adjusted between those materials with different properties, and this will align and give this Schottky barrier that are a Schottky barrier used for diodes. But this I will discuss more, and not just give this away, but I will discuss more in terms of Schottky barrier next week. But the Fermi level that are related, that is related with the last probability to find the last electron, they are is fundamental to construct a device, because when you give this interface, the energy of Fermi will be aligned with all the interfaces. So for instance, if you have here one and position. If you have one semiconductor that we call semiconductor P-type, this is P-type semiconductor, and we do a junction with one N-type. So what happens when we mix with one N-type semiconductor? This is not a junction. When we do junction, so it means that the distance is quite close of these two materials. The energy of Fermi level will be the energy of alignment. So it means that the material will give some energy and they will be aligned. But this I will discuss more next week, because it involves p-n junctions. So it's not so good my breath, but what I mean is that the N-type will be aligned with the energy of Fermi, so it will create a Schottky barrier here that will allow the movement in this side, but will block the movement in this side. So this is why to understand what is energy of Fermi is fundamental to construct devices in terms of charge transportation. So the Fermi level are related with Boltzmann distribution, because it will be different if we have a different temperature. It's temperature dependent, and at 0K, all the states below the energy Fermi are totally occupied, and in terms of 0K temperature, above energy of Fermi, these states are empty. So this will give us the fundamental basis of conduction. For instance, if we have metal, these states, occupied states and empty states, are too close. So one small quantity of temperature can give electron from the empty space to occupied space, from the occupied space to empty space. So this will rule the transactions between the gap of the material. So in terms of bond formation, bond formation, in case of carbon, the carbon, as I told, we have the s orbital and p orbital. So you know that we can have hybridization of the p orbital. So in terms of hybridization, we can also have sp1, sp, sp2, and sp3. So sp, sp2, and sp3. So in terms of energy, this hybridization will give different energy between the initial states. So here, for instance, if you want to analyze the diamond are hybridized sp3. So they have the s orbital and the p orbital mixed, and so they also have the energy quite close. In terms of distance, we can see that are almost the same energy for the all orbitals in case of sp3 hybridization. And these are zero, means that is the lowest energy that are the distance that give us the lowest energy of the electron. So the S and the P states will give a distribution of bonding and anti-bonding states that we call valence and conduction bond. And then this valence and conduction bond has energy around the 6 electron volt, and this energy is high than visible light, because the visible light is around 2 electron volts. So this transaction is quite high, and if we have different hybridization, for instance, this state distribution will be lower. So we will have states with lower energy than the carbon. So depending of the arrangement of the molecular interaction, the electron will occupy differently the states. So this I talked, and this difference in energy is called the energy gap. This, in terms of the valence and conduction bond, we will analyze if the material can act as isolator, semiconductor, or metal. So in terms of if the carbon had another electrons. They would be all over the core, and we will not analyze it. But in terms of carbon, we just have these two orbitals. So how we can distinguish valence band, conduction band, and the core levels of the electrons? So the core levels, they are in very low energy, and they are strongly bound. So they need high energy to eliminate these electrons that are trapped in the atom. So in terms of the core, if the electrons are more close to the core of the atom, they are more stick. So this is why we just work with the last state that are occupied, that we call valence bond. So the valence bond are formed by the bonding states that are related with the interaction with the atoms surrounding, and then this status can be occupied by the electrons, and they are occupied at a temperature 0 Kelvin. And the conduction band are the antibonding states that I showed with high energy, and they are unoccupied, or actually they are unoccupied with temperature of 0 Kelvin, but they can be occupied depending of the material's property and density of state distribution. So I talked it earlier, but here I'm giving one example of bond feeling, how we can feel the state of the orbital state, and then using electron. So one electron can have a spin up, another electron can have a spin down, and they are allowed at same state if they have one spin up and one spin down. So these spin are related to the magnetic property of the electron due to the movement around his orbital. So in terms of this, we will have Pauli distribution allowed, one, for instance, quantum number one electron up, one down, two electrons at the same state, but one up, one down. And the distribution are not allowed if this is this distribution here. So as we are, the electrons are Fermi, they are just allowed with different quantum numbers. So if they are two up, they are not allowed, neither two down or two up and one down. So we have this distribution. This is good to know because the distribution of the spin in the material will give the optical properties. For instance, to know if the one semiconductor can have a luminescence, and this luminescence will have a fluorescence or phosphorescence. It will depend of the the spin of electron in antibonding state. So this we will discuss later, but it's good to give this overview what is allowed in terms of electrons distribution and states. So each quantum state holds two electrons with different spin. Electron feel lowest energy states, so they started with the lowest, which means they firstly feel the core of the states, and then they go to the valence and the conduction band. In diamond, valence band are completely filled. This is the reason that diamond, for instance, is very rigid, because of there is no empty states. In the empty states, we will see that these are the fundamental for electronic devices, the empty states of the electron. And the conduction band are completely empty. So this gives the diamond the mechanical rigidness and also the transparency in terms of visible light. Okay, so we saw how can the states, atomic states, can generate molecular states. So in terms of density of states, these figures are very common. So in terms of experimental point of view, what we must understand in this is what is the highest occupied state in terms of one kind of energy, and what is the lowest inoccupied state. So this diagram is quite confusing. It's almost an art piece, but in terms of electron distribution, here I didn't talk anything regarding group theory, because this comes from the group theory. If you have it, you will see, but I will not focus on this. But each one is the wave vector corresponding of that K that I said on the Bloch theorem. And analyzing the lowest, the highest occupied state and the lowest unoccupied state, we can see the wave vector, which is the position of a wave vector. So in terms of this material, for instance, is here. And the transition of the electron goes from this one to this state. So this is the energy gap of the material. We commonly transfer this figure with this one that is more beautiful to understand, but what is talking there is if we have valence bond, a conduction bond almost at the same energy and or overlapped, they have this material with metal properties. So it means what? In the Fermi level, that is this dashed line here, we will have the electron fill this state, and just one amount of the energy, that thermal energy, can move the electron from valence to conduction bond. So they are free to move here and then return to the valence depending of the temperature. If the distance the energy of this increase, we will have some energy that we are prohibited to feel it, and we call this material as semiconductor because of the comparing on with the insulator, they have a small energy than isolator. So semiconductor and isolator distinguish itself just because of the amount of energy that is necessary to move one electron from valence to conduction bond. So for instance here, let me see if I talk everything. Fillet, valence bond, empty conduction bond. The gap magnitude that will rule the materials, electron materials properties, and the typical energy for insulator is around 5.5 electron volts. In silicon, for example, that is semiconductor is 1.12 electron volt. So semiconductor means that this energy here is the energy that we can use it from the visible light. So if the transaction can be used by visible light, so materials are semiconductors. Okay, so in terms of semiconductor, we can have a electron transition from the one state to another with different temperature. So temperature can disturb the transaction, and also I didn't put it there, but also one electromagnetic interaction. Optical excitation can also promote electron from the valence to conduction. This is the reason I put it. And in case of room temperature, semiconductors show finite conductivity. So they have a limit of the conductivity because of the number of carriers that are free. So the semiconductor strongly depend of number of carriers. So this is the reason why the semiconductor cannot transport without any doping. And then also at the room temperature, the insulators remain highly resistive. So this is this behavior can be applied to different duties in terms of devices. So if we have, for instance, we want to laminate the device, do some encapsulation, we must use one insulator because we don't want any charge to be conducted outside of devices. So this also nice to investigate and applying the isolators materials over the devices. The electrode behavior is strongly temperature dependent. So it means that if we are analyzing one electrical property of the material and we want to know, for instance, his mobility or his number of carrier, we must evaluate it in terms of temperature, because if we have a high temperature, we will give energy sufficient to have more carriers. So the number of carriers is proportional of the temperature. So, for instance, today I did one synthesis of one metal, and then I want to evaluate his conductivity. I must evaluate his conductivity in terms of temperature, because today the weather is around 10 degrees, but if I measure the same material with in summer, for instance, they will have a different temperature. So the number of carriers will be more, and also the conductivity will be more. So I didn't have better material with higher conductivity. I just evaluated with temperature different temperature. So in terms of charge transportation, and if you want to evaluate this phenomena, charge trapping, charge transportation of your material, you must at least go to high temperature and low temperature. So this the number of the carrier concentration will strongly depend on the Boltzmann distribution. So it is a Boltzmann distribution of a number of carriers. So as we talked, the metals, the valence band and conduction band are overlapped, and the energy Fermi level are both in the valence and the conduction band, or they just have a bit, I didn't put any figure here, but they just have a bit small separation in terms of just a small quantity of energy can move the electron to the conduction band. So I didn't see that my figure covers here, but what we want to see is that in metals we have electrons that can move freely into the material. So the free states are they are very fundamental for the charge transportation, and we can measure the conductivity of the material in terms of number of charge transportation and mobility that he has. So it depends of the number of carriers and how they can move freely. This is the mobility of this electron, and this is the charge of the charge of the electron. But what means the mobility? If we have some structure that is not ordering, there is no ordering, we will have some resistance that avoid the mobility of the electron. So the conductivity, if we have, for instance, in terms of high inorganic materials, that we can have lattices, ordering, and crystal organization. With more organization to the space, we can have more distribution of the electron over the space. When we analyze in terms of polymers, we must analyze the conjugation, how we can just do the distribution of the conjugation over the length of the polymer. So organics, they can behave differently to inorganics in terms of that. But one that I can anticipate it for you, one of the main reasons that nowadays we are investigating organics is because the organics can have more free empty space states on the conduction band, so they can be charge trapping, but they also can be easily filled if you have electron field or if you have any other distribution. So the organic, they can give more number of states than inorganic. This is the reason that we also want to investigate more organics. Even that they are chaotic, they are they need a low energy to fill these states. So the conduction. So if we have this metal here and we apply energy potential between this material, what we must expect? The electron, they are accelerated under this electron field. So there is here. We design the electron here, and this is the potential bias. If I apply, I want to see the conductivity of the material. So here I will apply one. I will grab my my material. I will apply one battery, so it will create. I did it. Yes. It will create an internal field here, and this field will, depending of the empty space that I will draft here as this box, the electrons from my bias goes to the bias and fill the vacancies of the empty states that has in this metal, for instance. So depending, if I increase the voltage, I will increase the mobility of this charge. So this charge has some mobility, for instance, in this direction. Actually, it is another direction. I rotate it. So if I increase the voltage, I will increase the mobility, and then we can measure this mobility also in terms of potential. So if we apply different one electro potential in your material that are metal or semiconductor, the state is that there must be empty states, so we can fill it with electron field, and generally, in terms of semiconductor, if we can fill the conductor band, we can have the movement of this electron, because they are not in the interaction with the crystal lattice. There is lower interaction with crystal lattice, so he is free to move. In this movement, we can predict using velocity in terms of the charge transportation, and see how the potential that I applied are correlated to the velocity of this charge. So it will give us, is not here, is in another slide, but it will give us how the mobility are related with the electron field of that I applied. So in terms of the structure that I told you, we saw that the energy in this here, the energy of the density of states, they have different shape with the distance of the atomic distance. So this difference, they are really related to the effective mass of the carrier that we are observing. So in terms of the electron, so the carrier is electron, so they have effectivity mass that be not the mass of free electron, but the mass of the electron associated with the materials composition, and also the scattering of the electron inside the lattice. So this energy has this different shape that we saw earlier, and will be related to the effective mass of the carrier. The electron also has different effective mass than the hole. So if you are analyzing the hole, the effective mass of the hole is higher than electron. They have different mobility, and they also different transitions. So we saw in the density of states that those energy is anisotropic, which means that here there is one shape, and here there is another kind of shape, because here is valence conduction bond, and the effectivity mass of the electron is different than the hole, and also the mobility is different. So the energy is anisotropic and depend of the direction that we are analyzing. That is that key direction. So in terms, what I want to say to you, here, for instance, this anisotropic distribution of states, if we want to analyze the energy transaction between the highest occupied state and the lowest unoccupied state, we must understand that the position of key vector maybe are different in terms of the lowest unoccupied state and the highest occupied state. So if the position in the band density of states are different, it means that the highest energy is not at the same position with the lowest energy of the conduction band. So it is different in terms of key vector, because of the scattering of the carrier, of electron phonon coupling, and another several things that could be effect. So in this way, we can distinguish the energy gap and call direct energy gap and indirect energy gap. So the transition direct means that the conduction and valence bond has the same position in the lattice, so we don't have a difference in terms of energy, this is more visible in the inorganic compounds, and this is more visible in the organic materials because of the electron phonocoupling. When there is a lot of scattering in organics, so they have indirect energy gap. But what we want to understand here is that has two different semiconductor transitions, and this can be this will directly affect the performance of material when we apply it in devices. So, for instance, direct band gap, they are usually used for LED, OPV, and lasers because we don't lose energy here. If you want to, for instance, has one LED, this transaction here, you can apply electron field, fill this bond, and this bond, depending of the empty states here, will be recombined and emit one light. And if we have this kind of energy gap, that is indirect energy gap, we will lose too much energy to the thermal conversion because of the interaction with the lattice. So this is the reason that directed band gap is preferable, but as we know, we can also use indirect band gap to construct LED, but it's preferable for LED. And the indirect band gap is usually used for logic and power devices because we can trap the electron easily than direct band gap. Okay, so some things I talked, and then now I will talk again, but it's good to give you an overview. When there is one perturbation, it means that there is light-matter interaction. We create in material one hole that is the absence of electron in those states. So we have electrons, that is one particles, and we have holes that are quasi-particles, and we can move this hole in the material and predict his mobility, and use his mobility to also manipulate the charge transport of the devices. For instance, in OPV or perovskite photovoltaic devices, we have electron transport layers and we have hole transport layers. So we must distinguish those two kinds of carriers. Each one has specific properties. So we cannot use the same material as electron transport and to the hole transport because they have different properties. So in terms of the holes, so the electrons goes to the high energy, and the lowest state gives will be empty, and we call this empty in the lowest state as hole. So the electron appear in the conduction bond, and empty state appears in valence bond that we call hole. In terms of Coulombic interaction, inorganic, they have because you can think electron is negative, hole positive, so they are binding and do what we call expo, because they have this bind of energy. In inorganic, this difference of the energy of the expo is small. So when we create this expo, is almost that we have electron freely in the material. But in organic, for instance, due to that different in the scattering and the charge dropping and the dielectric properties of the organics, they are too strongly bind. So, but in this case, we are analyzing inorganic, so we consider that electrons goes and be free and are free. So if we have one electron in valence bond, in conduction bond, we have one hole in conduction bond. So the number of electron and hole are the same, are equal. So here, for instance, we have this material with this density of state distribution. We apply laser, so the electron goes from valence bond to conduction bond, depending of the energy of the laser, and if have one state available here in terms of density of state, we can see that there is laser state available here. We create one electron in the conduction bond and one hole in the valence. So if we use one photon, we will have one electron and one hole. If we use in terms of number the photons, we will have more n electrons in hole created. After the electron going to the high energy, if the energy of this electron is not the energy of lowest position of the state, the electron do not emit light with this energy. He will give some organization of the lattice. So he, for instance, you give light to the material heat, and then he will give us a light back with energy lower than the energy of excitation. So it will directly depend of the density of states and the correlation between the coupling of the electron and the lattice of your material. So right after excitation, the electron goes there, and then if you had one thermometer and measure the temperature, you can see that locally there is high temperature, and then he goes to the lowest temperature here in terms of the state distribution, and recombine emitting light, because this is not one equilibrium state, is quasi-equilibrium state, because the electron do not want to be on the conductor bond, but return to the valence bond in terms of semiconductors. So here is what I I drafted. And what we will discuss it more in the next week. But in terms of junction, when we applied light, we created one hole in the valence and one electron in the conduction band. And when we do junctions, we can move these free charges that are free electrons and free holes in different directions and created, for instance, photovoltaic effect. But what I want to say now is electron here has mass, has charge. Hole here has also mass, has also charge. His charge is opposite, but his mass is different than the electron. So electron has effective mass, and hole has effective mass, and this mass effective is different because the mass is related to the inertia of the particle inside the material. So in terms of hole, here we have a lot of atoms that bind the hole, and we don't have a lot of atoms in terms of energy to bind this electron. So the effective mass of the electron is lower than the effective mass of the holes. So holes, they act as a quasi-particles. They are not particles, but they have a wave vector, they have energy, they have a charge, and they have effective mass, and the mass is different than the electrons. But why the effective mass exists? They exist because of the interaction with the lattice of material, and also because of the different inertia of the carrier inside the material. So we don't have any more free particles with free like free particles, but they are inside the material. You depend directly on the material's properties, and it will affect the charge and mobility and also the performance of devices. Here, I put this slide. I didn't remember. Let me see here. How we can, it's just to give for curiosity, how we can measure the effectivity mass of the carrier. So we use group velocity, we apply electrofield, and we can measure the effectivity mass of this charge depending of the barrier that we construct also when we want to measure. But I will not give it too much time on this. What I want to say is, as I told, the effective mass of electron is different than the hole. And if we have holes close to the surface of the highest occupied state, we have heavy holes and light holes. It means that depending of interaction of the particle with the materials, it will give some inertial mass differently than when we analyzing the materials with different energy state. So the holes are fundamental to rearrange the states of the materials and give different available states also. Electrons, for instance, they have just one specific mass and do not change it. So if we have heavy holes, the curvature of density of states will be lower than if we have light holes. So when we have holes more heavy, we have a more almost flat bond in terms of the shape of the density of states. So this is what I said. Real semiconductors often have multiple valence bonds, different curvature, different effectivity mass. We have heavy holes and light holes. For instance, this semiconductor that gallium arsenide, we can have a different length here, for example, his density of state, and we have heavy holes and light holes in lighter hole here. So there is difference in density of state because of the effectivity mass of the hole. So the shape of density of state will be also different in terms of the effectivity mass. So I talked more about the density of state in correlationship with the how we can know if the material is semiconductor, is metal, how we can predict his behavior in terms of lattice. And but in terms of semiconductor, general analyzing inorganic semiconductor, they are intrinsic. What means intrinsic semiconductor? That they have no defects. They are not. They are. The chemical bond can distribute electrons to his neighborhood, and then the valence bond will be full and the conductance bond will be empty, so we don't have carriers free. So to have movement, we must to have liberty. So if we don't have free charge, we don't have movement. In terms of silicon, what this can be understood. Electron hole pair, they are thermally generated, and this electron hole pair, they are just intrinsic, and they not can, if there is no perturbation, they cannot have any movement. In terms of number, as I said, and in terms of Boltzmann distribution, we can also predict the number of carriers that can be created over perturbation. But we also can create one charge with extrinsic semiconductor or doping. So if you want more mobility in your material, you generally create doping side of them. So how we can engineering conductivity, even that in semiconductor materials, we intentionally introduce some impurities that we call doping. So this doping can control the number of carriers and also his conductivity. We can we can distinguish two kinds of doping: N doping type and P type doping. So it means that we have more electron rich material with type N type, and P type we have more hole rich material. So sometimes we think about mobility, we just think about electrons, but not just electron can be used, but also we can have the movement of the holes. So for instance, here we have the silicon, and the silicon in terms of bonding, he can bond with itself. And forget this phosphorus for one moment, but if this is silicon, we have intrinsic semiconductor, which means that every electron from the silicon is shared with his neighborhood silicon, and everything is perfect. There is no any impurity, any free charge here. But if we dope it, during the crystal growth of silicon, we intentionally dope with different material. For instance, here the phosphorus. The phosphorus, he acted in group 5 of the element table. And then will be one free electron of phosphorus, free without any bonding, because we have 5 bonding available to phosphorus, and silicon has just 4. So it means that we have one electron without do anything, just free. This electron free can move through the lattice easily, because he is not bind with nothing doing to this doping. So depending of the kind of doping, you have a different carriers, and you have also different movements of carrier inside this lattice. So if we don't want to see one doping with phosphorus, but we want to doping with boron. Boron is the material from group 3, and he acts as a scepter because he needs 3. He just do 3 bond, but silicon do 4. So it means that we have one hole here in silicon that can be moved around this lattice. So depending of element that we use, we can create different conductivity in the material. So in terms of the bond distribution, what we created is we can move the energy, the firm energy, depending on the kind of doping that we used. For instance, here we doping with one acceptor. So we created one state with lower energy than what we had earlier without any doping. So it means that there is this set here, ultraviolet from energy if the semiconductor is intrinsic, and if we dope the semiconductor to have one transition from valence bond to conduction bond, just visible light can be used. This figure is not too good quality, but we can see this movement in energy, Fermi energy level. So in terms of semiconductor, the Fermi energy level means that the probability to find the electrons in terms of semiconductor is between the gap, is the half of the gap. And if we dope with some donor, so any type doping, this level of energy Fermi will be moved to higher energy than without any doping. And if we dope with P type, it will be moved to lower doping, to lower energy of energy, Fermi energy. Okay, so in terms of the doping of semiconductor, we can create carriers. So the carriers will be used to give movement in the material. And we must distinguish the carriers in the material as majority and minority carriers. It means if we have an N-type material, that is for instance, silicon doped with phosphorus, we have more electrons than holes. So we call carriers majority as holes, and we call the minorities of carriers as holes. In case of the p-type, where we have more holes in the material, the majority carriers are holes, and the minority carriers are the electrons. So why we must distinguish, as I told you earlier, the minority carriers, they also impact in the diffusion of the charge inside the material that is used in the device. So in terms of the energy of the material, we don't have this movement in energy just with doping. We also can have this control of the energy of the material in terms of confinement. So it means what? If we have some technique that we can grow one material, in this technique we can control, for instance, the distance of the material. If we somehow reduce the distance or do some confinement with one potential, we can also create some energy between these states. What I'm saying with it, for instance, if we have this league, the gallium arsenide, and we want to construct one quantum dot, for instance. How we build one quantum dot, one devices on quantum LED, for instance. We can grow the material with one property, and then we change his property with another kind of material with the same league but with one doping, and we can, without his doping actually in this case, but we can grow the material with a specific distance. For instance, I want to build just 10 nanometer of gallium arsenide. So it means that I will confine the electron inside this potential. So we can build this quantum well or quantum dot using this confinement, and we can just limit the energy of electron inside this potential. So we can usually, actually it's quite commercial already, the quantum confinement. And if you want, for instance, you grow the material not from 10 nanometer, but 15 or 5 nanometer, you decrease the energy and you increase the energy respectively. Here is another example of silicon. Here's a silica, here's a silicon, and here's a silica. And we can grow this channel here just in terms of thickness. If you want more thick, you have more liberty of the electron. So the electron will have, I don't know if you remember, but the strain, like a strain behavior of sting behavior of inside the one potential, and if we increase this distance, they have more energy available, and there is the energy available. They have low. We will have low energy than if we want to more tight confinement. We can also see it in nanoparticles. It's quite popular. So if we have one nanoparticle with 2 nanometer is different. If we have a nanoparticle with 6 nanometer, because of the light management inside of those potential. So it is quite important to understand that we can somehow play with optical properties, not just with doping, but also with confinement of the material. So if the confinement is lower, the distance, the energy will be higher, the optical transitions will be higher. For instance, here, the nanoparticle, the small nanoparticle, the gap between the excitation and the conduction band is higher than one nanoparticle that has a higher diameter. I talked regarding Fermi-Dirac distribution. Just here I give this extra slide in terms of the number of carriers. So the number of carriers will be also involving in the quantum confinement, but we can also we can know if the distribution of the energy states are related to if they have n-type or p-type, but the Fermi-Dirac distribution, they can also be different, as I told, if the temperature is different. So if we have a different temperature. We have carriers with a different position in this state. So the doping will influence the quantum confinement, and the temperature also influence the quantum, the energy gap of these transactions. So it's very important to analyze the semiconductors in terms of temperature, in this case of heat. One thing that we discussed, but I just give I will accelerate because of the time. When we have carriers, even that is minor carriers, or majority carriers, electron or hole, depending of doping, and we want to understand how these carriers can move inside the distance that we defined in the device. So in terms of it, we must know the mobility of these carriers, and the mobility of the carrier can be measured using two kind of experiments using charge limited for spatial charge limited current, which means that we will have some block current and measure the charge that can be transported. But we also can use it Hall effect to measure this mobility. And the mobility, as I told, is quite different if we have semiconductor with N-type, P-type, majority type holes or electrons, and if the holes between the holes and electrons is also different. So in terms of how we can measure the conductivity and resistivity, to know the conductivity of material, but we must understand that conductivity of material is a combination of number of carriers that are available and also the mobility of them. So in the laboratory, we usually measure the resistivity, which can be related to the thickness, but correlated with the conductivity of the electron of the material, and this conductivity can be correlated with the mobility of carriers. But it's important to know that the mobility is a combination of both carriers, not just electromobility. And also the mobility will be influenced by the scattering of the material and the property of material to have electron phonon interaction coupling. I think I just I will give this information here because I must have this figure. I didn't put this figure earlier, but when we want to measure the conductivity, we just use we apply one potential and measure the current, and we measure the current that is out of the material. So what I saying that the mobility inside the material is ruled with the movement of the holes and the electron here, and also the rate of recombination and generation inside the material. So this is quite nice to see. I can came back next week with this discussion, but this will rule the diffusion of the carrier inside the material. In terms of if we apply electric field in material, we have this electron and hole movement. So if we apply one electric field that's too high, we have this current saturation. That means that all the carriers that you move inside this potential, it reached the another contact. So it will depend on the materials properties, but every material has this velocity that are saturated, and we can fit it and find its mobility. In terms of Hall effect, when we apply magnetic field perpendicular of the movement of the electron, we created one force using Lorentz force, and this force will created inside of the material one current that can be opposite or can, depending of the arrangement of material, but can also be can also affect on the current that you are measuring in the electron field. So the Hall effect is the technique that we usually use to measure mobility of the departure of the carriers, because we can distinguish the carriers if we shift the polarization, the direction of magnetic field. So we can using Hall effect, we can screening one kind of the carrier of your material and also know his mobility. So I think these slides I will use in the next week, because I will not. I don't want to talk too quickly on this topic, so I will return these three slides in the next week. So today, what we understand with this bond formation and the correlation with material, that density of state that usually used through simulation is useful to know if the material has the relationship of the thickness of material, the transactions between the states, and all the states that are available. We can also use density of states, know the mobility and the effectivity mass of the material. But for us, it's useful to know if there is some semiconductor property or metal or insulator property. Fermi-Dirac statistically rules the distribution of electrons in those states, and the position of the Fermi level can be adjusted if you have a doping or not in your material. When we perturb the semiconductor, we create, when we perturb the material, we create a charge that we call quasi-particle hole, a charge with positive charge, one positive charge of electron inside your valence bond. This hole has energy, has effective mass that will affect the material's properties. And also, if we want to move the position of Fermi level, we don't just need to dope the material, but we also can use quantum confinement through nanoparticles or through quantum walls. And the Wouk behavior will be ruled with low dimension physics that is the same as string in the potential. So everything that we learned today is regarding the engineering, the bond structure of the materials, and this will be useful when we want to see how electronic and optoelectronic devices works. Okay.